for introduction. Thank you very much for having me here, which is a great pleasure. Sorry, I'm slightly tired, so I'm not sure, but we'll see how the talk comes. So I'm going to talk about the formation of T-structures. So it's a bit formal as a subject. I'll try to give some motivation a bit later during the talk. But for a moment, I just want to mention that this is a joint work with Alex Perry and Paolo Stellari. But it's based on a long project together with Chuni Li as well and Xiaolei Zhao. And unfortunately, it's taking longer to write this paper, and the reason is that it's very technical. And so I'll try to show you a bit the technicality that we are dealing with. But let me start with the statement, and then I'll explain it, and then I'll say some motivation. So the statement, it's actually a conjecture. I go there. No, but faut baisser le volume. Sinon je. Okay, j'arrive. So it's a conjecture that we have with Alex and Paolo. And okay, I go. And the conjecture is the following. So I start with S, some nice base scheme, where nice. Well, there are some assumptions nice, but nice, for example, means separated finite type over a field, but actually we allow also things in positive characteristics, so the key word here is excellent. And separated. But anyway, anything which is good over a field or over Z, for example, finite type. And then let me first state the geometric situation, and then we'll do the general statement a bit later. So let me assume that X over S is some proper and flat scheme. Then the statement is the following. Let me state it. So then there exists an algebraic space which I'm going to denote by Tx over S, which does the following. The key property is that which is étal over the base, but nothing else. So it could be it will be kind of horrible algebraic space, but it has the property that we like is that which admits a factorial bijection as follows. So this is, let me denote the associated functor by T with slightly curly, so X over S, which if I plug some spec of A, this is the following. This is going to be, let me first write it and then explain. So these are bounded T structures on the bounded derived category of coherent sheaves on the base change X to A, which are the property that their heart is Noetherian. And the spec A, it's something which is over S, which is of finite type. Okay, so that's our statement, the conjecture at least. So let me explain slightly what it means. Let me call this formula star for later use. So first I want to explain also what are T-stirps in a second. So I want to explain what bounded T-structure is and what Noetherian. So concretely what it means is statement, it means the following. So the key word here is étal. So this means that if I have a family over some affine base, and I have a bounded T-structure with Noetherian heart on a point, this conjecture is saying that you can always find some T-structure on an étal neighborhood. Okay, so you can always extend it from a point to an étal neighborhood. So that's what it means. Okay, so that's a statement, and sure. Maybe it's locally finite type, but yeah, I think we know nothing actually of this thing. But yeah, maybe it is locally finite type. possibly. But it's highly horrible, this thing. Nobody guarantees that it's separated, for example. It might be as bad as possible. The only case where it's not so bad is when, for example, S is a spec K, for example. Then it's a scheme. Clearly not a finite type, but it's still a scheme. Okay, so just an étale scheme over a point. But that's the only case that we know something. But yeah, it's probably local finite type. I don't know, actually. Unclear. Okay, in any case, so this is a conjecture, and yeah. So there is it's only an algebraic space, unfortunately. So no more than, no, we cannot say the scheme. And the way that we prove it is by using, I will see in a second the proof actually, is using Artin's criterion. So that's what we check. But we don't know if it's a scheme, and in general somehow, it's only a scheme when as I said, when S is very easy. So like a point. That's the only thing we know. And this bijection, this is important, we'll see later, it's only true for finite type things. So that's very important. So if you base change to something randomly, we don't know what it is. We only know that there exists a functor which has this description on finite type schemes, which are affine. In general, we know nothing.
Yeah, I mean, of course, you lose the Newtonian proof.
That's clear, yeah, because we don't know anything. I'll comment in a second. You will see what is the functor, and you will see how it's defined, and we'll see what we can prove on this. So the main statement is that we can almost prove it, but we prove just one result, which is what I told you, that you can deform something, at least formally. And that's for application is pretty good for us, but this will be nice for the future development of the theory, and we cannot prove it. I'll show you what this problem is. So let me first make some explanation. So the assumption on the base, for example, why do we need all these assumptions? Because, as I said, we want to apply a few results. For example, we want Artin's criterion, so we want some sort of nice property on the base. But also later on, we need some results on finding some nice regular cover, and so that's why we need this assumption. But anyway, so that's one thing. And let me say briefly what is a T structure, since the whole talk is about this. Though I think all of you are confident with. So a T structure, so let me start with a category D. We'll see later, some triangulated category for the moment. And so about the T structure, generally we denote by tau. So these are just a way of writing complexes. D as it would be a category of complexes. These are complexes in negative degree, these are complexes in positive degree, and with the property that complexes have. So for example, I want that D is smaller or equal than 0. If I shift it by 1, this I want it to be still smaller than 0. I want that the greater than 0 is just this category here. And then I take all the one which have no morphism between them. And the third thing is that for all non-zero object in D, I want to write as complex, as extension of complexes. So with obvious notation. Smaller or equal than 0 goes into E, goes in T greater or equal than 1. Okay? With the notation, so this will be in D greater or equal than 0, shifted by -1. Okay? And this will be in D greater or equal than 0. Okay, so that's the standard definition of T structure. It's not super important, and the only important thing to do for later is that everything is determined uniquely by this thing, because this one will be defined as orthogonal, and so the whole point is to construct such an object somehow. So the example here we start with, and that's a perfectly nice example, if D is D dx, then an example of D smaller or equal than 0, these are just complexes in negative degrees. Okay, so that's the example we want. This is a perfectly nice example because I will say in a second. So the only thing, yeah, in non-positive, thanks. Yeah, in cohomologically. Yeah, thanks. Yep. So that's the thing that we have. And so why do we care? Because when I take the heart associated to something which is d smaller or equal than 0 intersected d greater or equal than 0, this is the heart. And the key point is that it is in abelian category. So in particular, it makes perfect sense to speak about sub-objects. And so it makes perfect sense to say what to be Noetherian means. And so Noetherian means that, the usual condition for that any ascending chain of sub-objects will stabilize. So Noetherian makes sense. Okay, so that's the word Noetherian here. And bounded, so bounded, there are several definitions in the literature of what bounded means. For us, bounded means bounded and non-degenerate. So let me explain a second non-degenerate, since we're going to use it a bit later. So non-degenerate, having written a category as complexes, I have a notion of cohomology, exactly as for standard complexes. So non-degenerate means that if a complex has zero cohomology, then the object is zero. Okay? And bounded means it has bounded cohomology. But I can put the two of them together by saying that D can be written as the union of A smaller or equal than B of D greater or equal than A intersected the D smaller or equal than B. And so this is equivalent to both of them. Okay, so that's the statement, and now this should be clear. I have something of finite type and something Noetherian, so this is Noetherian, this thing makes perfect sense, and now this is the statement I want to prove, at least, this conjecture. So let me make a few remarks. I have other categories to work with, we'll see a bit later. For example, perfect complexes. Perfect complexes do not have these structures, so that won't work in general. And I can say, why do I have this assumption of Noetherianity? We will see in the proof, but without this assumption, the theorem is clear, the conjecture is clearly false. And so the classical example is P1. P1, you can find some over a point even, you can find a continuous family of these structures. So here we really want something which is a tal. Okay, so that's the whole point. And so third part of the explanation is that why do we have this conjecture? Is because this was very much inspired by, say, compare with a result, with a theorem of Bellman's, Okawa, and Ricolfi on semi-orthogonal decompositions. Okay? And so what is the theorem? The theorem is the same exactly as we stated here, but instead of wanting bounded T structure, I want a semi-orthogonal decomposition of the right category of a certain length. And so the same conjecture now is a theorem, and there is some sort of duality between semi-orthogonal decomposition and bounded T structures. And we will see that our method actually does apply also to semi-orthogonal decomposition, gives a reproof of the theorem by Bellman's, Okawa, Ricolfi, and also generalize it and proves also a conjecture by them. So in that case, it's really a theorem, the result. And I will show you why for T structure it's just more difficult to prove this statement. Sure. So S, the only condition I need is that it's excellent. So excellent because I'll show you. I need to apply Artin's criterion. So I need this condition that if I take the map from a local ring to its completion, I want this map to be geometrically regular. But then also in the proof, I need to find some resolution of S. And so these I need to find some so-called H cover, which has finite global dimension, and they need some excellent property. And separatedness I need because I will need it in general to have some nice... separated I need because I want that the category of quasi-coherent sheaf to be the int category of coherent sheaf. Anyway, some technical condition. But no other condition. For example, I'm allowing, this might be useful, although we don't have any application for that. We're allowing mixed characteristic, for example. So that could be something that... but besides that... no, and I think unfortunately for this kind of yeah, maybe you can weaken it somehow, but But that's the only thing, yeah. So for the moment, but in this kind of statement for algebraic spaces, generally that's a condition, some weakening of it at least, but some condition you need. Yeah. So let me say, maybe comment about this. So what is the idea of the proof? So what is the approach to this conjecture? And so the approach is to use Artin's criterion, which let me remind you briefly. So what we need to prove? So we have this definition. So we take this star as our definition. So this is the defined of a scheme of finite type. The first thing which is absolutely not clear actually is that this is a functor. So this means that why if I have a map between two affine schemes over S, there is an induced map on this definition. But this is true, and this is work by Polishuk. I'll comment in a second later about this. Let me first write what we need to prove. The second thing we need to prove that this is a sheaf with respect to some topology, let's say the Tal topology. And the second condition, so in this definition, we need to prove that this is a fundamental property, that this is locally of finite presentation. And so what does this mean? So this means the following. So let me go here. So this means that, oh sorry, let me go here, I have more space. So this means that if I take this thing and I do a co-limit, sorry, of algebras, and this thing is still an algebra of finite type, then this is the same thing as the co-limit of the sets. Okay, so that's a condition. So this is a locally finite presentation, and for the moment, these three conditions, it's enough to check them for this kind of objects. Okay. Because it's a well-known an epsilon thing that if I have 0, 1, and 2 on all spec A over S of finite type, like this one, then okay, with some epsilon, it's a standard result. I can extend star to all schemes. Yes, and the definition is just this one actually. So once I have this definition, I take your scheme, write it as limit of spec of something of finite type, and then this is the definition. But we don't know anything else, so that's the only thing we can do. So we don't know how the scheme is defined, how this functor is defined. We only know that it's defined intrinsically as co-limits of those things. So we don't have anything more except that it exists. Yeah, so that's a problem. But anyway, so we can extend it, and once we have 0, 1, and 2, we also have 1 and 2 for tau x over s extended in this way, still satisfies both 0, of course, but okay, 0, 1, and 2. Okay, so that's all good. Once you prove these three properties, then it's good. And the key property, which is property 3, so I finish the statement, is the formal deformation statement. So if I have a local Noetherian ring, which is emadically complete, ring, with the property, if you want, that this thing is nicely undefined. So the thing that if you take the closed point B mod M inside spec B over S, so this map here, I want it to be of finite type. Only the composition, otherwise. Then the key statement is the following, is that T of X over S applied to B, this must be, I have a restriction map into the, by functoriality, into B mod M, and I want this map to be bijective. Okay, so that's the statement number 3. So again, what it means concretely means I'm giving you a T structure with all this property over the closed point. There is a unique way to lift it locally when the ring is complete to the whole family. Okay, so that's the statement. Okay, so formally et al. Okay, great. So if so the statement of Artin criterion is that if 0, 1, 2, and 3 holds, then the conjecture is true. Okay, so that's the theorem.
In the case where B is not a finite type, you just don't know what this means, right?
That's correct. I don't know what this thing means. That's exactly. The point is this one. So I don't know what is this. And in general, it's not a finite type, and so I don't know what is this. So the whole point, and that's why we cannot prove the conjecture, is that we don't know what is this. Exactly. Yeah. So that's somehow we know it defined by this condition. We don't know what it is. Yeah, that's we arrived to that. So the first statement, that's not so hard, also because it was already proved. So this is these are results by Abramovich, Polishuk, and then there is this beautiful paper by Polishuk, by himself, which actually started the whole theory in some sense. And then and then we had to do a small epsilon because that was the first paper, so we need to add a few more extra things. But it's essentially his work is that 0, 1, and 2 hold. Okay, so that is good. So it's a functor, and that's a key part actually. This is actually the hardest part. And but this is really his work somehow. That's really, and these two essentially he proved it. But this is actually not so hard to prove. Okay, great. And so that's where we are. And now, of course, the key part is proving 3. And as Sasha mentioned, we cannot prove 3 because we don't know what this is. But okay, for us, it's we can prove a weak form of this, which is enough for all application, which I'll mention in a second. So here is main theorem. So this is again with the 3, with Paolo and Alex. So let's take Bm as above, okay? Now I define something which I would like this to be. And so I define as follows. I define T of xs prime of B as what I want. So I define it exactly as what I would like to be. So these are bounded T structures on dB bounded coherent xb with Noetherian heart. So we don't know that T prime is the same as T. Okay, so for us T is only defined by this formula, and this is what we would like to be. Still, once I have this one, I still have a map which is a restriction map in B mod bon M, and what we prove is that this map is bijective. Okay, so we do prove that you can lift a bounded T structure with Noetherian heart at least at the level of, at least the formal level.
Imagine that X, the map from X to S is an isomorph.
That's correct, yes.
Your XB is just B, right?
Your XB is just B, that's correct, yeah.
So if you start with a standard T structure on the central fiber, I mean the T structure it should deform 2 should be the standard structure on GB of XB, and it is not Notarian, right?
Sorry, say again, it's not?
It's not Notarian if B is not Notarian. XB is B, so this is a standard structure of GB of B.
Yeah, but the base is always Noetherian, in this case. The base is Noetherian. Sorry, this is the question. The base is always Noetherian. It's excellent. Yeah. Everything is yeah. No, everything is well defined. That's also what excellent means Noetherian as well. So everything is sorry. Yeah. So anyway, so this is a theorem, and for all application, this is more than enough for us. The whole statement somehow is telling you that I can lift a T structure the theorem will tell me that I can lift it et al. And so that might be useful for later on, for several things, but for most of application, for us, formal level is enough. Okay, but unfortunately, yeah, we cannot prove the theorem. So that's the conjecture. But okay, that's so this is a version of property 3, but it's not 3. Okay, yeah.
Is T prime a functor?
We don't know actually. Yeah, we don't know. Yeah, indeed. The findings like these, we don't know if it's a functor because we don't. The base change. This thing of functor, right, is resulted by Polishuk. It's very tricky to prove, right? You need to prove that you need to use finite type because you reduce to Pn. You reduce, and so that's actually the whole problem. Somehow we don't know we don't know if it's a functor. No, but we do know that there is a restriction map. That is fine. So from this guy to this guy, there is a restriction map. So it's functorial in this sense, but in general, we don't know.
You cannot talk about functorial map if the source is not a functor.
That's correct. But we do have, but we don't know if this definition will define a functor. No. And actually, my explanation is that it's not actually in general. I don't think so. But in this case, it should be true. Okay. Hopefully, if the conjecture is true. Yeah. So let me make a few remarks about that, since you asked. And so, yeah. So what is the hard part, and why semi-orthogonal compositions are easier actually? And so the reason is the following: is the reason of where objects are defined. So if I write B as a limit, as a co-limit, sorry, of some algebra of finite type, the only thing I have to prove that the T structure we obtain is coming from something defined on a lower ring. But, so remark, let me make two small remarks. So the question is that if I take B as before, and I write it as a co-limit of some A alpha, so what I need to prove? I need to prove that tau prime x over s in B, so this is the same as the co-limit of this thing. And so this means I have to prove that each object is defined on some globally defined A alpha. So I know that each object is defined on A alpha, but I want a uniform thing. And so the reason why these people can prove it on semi-orthogonal composition is that semi-orthogonal composition only depends on finitely many objects. So I take these finitely many objects, I lift them all to a certain alpha, and then I'm good to go. While a T structure depends on infinitely many objects. So each object can be lifted to some A alpha, but maybe the A alpha are infinite. And so that's the issue that we have here. And so that's what we need to prove. And let me say that a baby case, which is still will be very useful for us, but we cannot prove it, is the case of a DVR even. So I take a DVR, I take a completed DVR, and so the question is how to compare tau x over s of R and tau x over s of R hat. And so actually maybe let me put the tau prime here. It doesn't matter. And so yeah, so this is the same as tau. This is tau prime. And so yeah, so the thing we will want to do is that this thing maybe is a bijection. Maybe it's a bijection up to something et al. So we don't know. Okay, so already this elementary case, it's so if you have a T structure of the completion of a DVR, we would like to extend it to a DVR maybe, but we don't know. Yeah. Ah, yes, that's a priori unclear, a priori. A priori, it's not even needed, actually. Maybe it's just a Zariski condition. So we don't have any example where this thing is not a scheme, actually. Yeah, so indeed, maybe in this case, it's actually true. Maybe somehow if I have a DVR and I have something on the completion, then you can always lift it. We don't have any example. But okay, at least for proving this theorem, somehow the only way is Artin's criterion, and that's just is telling you that there exists an étale cover. More than that, we cannot say. But yeah, you're right. Actually, there is no reason. And a priori, yeah, I don't know. Yeah. And even for similar orthogonal compositions, we don't have any example, I think, where we know. Yeah. Okay, great. So that's a remark. So similar orthogonal composition, the same approach works and proves the theorem because it only depends on finitely many objects. Okay, but that's not enough, unfortunately. So we need okay, now I'll present how to prove the main theorem. But for applications, so the application we have in mind are geometrical applications. So it means that we need also stability condition, which I won't talk about. But unfortunately, or fortunately, this setting is not enough for our application. So we need something slightly more general. And so I'll try to show you, and then I'll give an idea of the proof, actually, of that. So I need something slightly more general, especially, for example, some application that we can have, for example, is proving a conjecture by Evgeny and then Sasha, and that needs really a family of categories. It's not just a family of schemes. Also, other application we have in mind is to K3 surfaces of 2 hyperkähler, and also there somehow we do need some weird setting, which is this one, unfortunately. So let's try. Okay, so let me do this setting the more general possible. I will redefine what is the functor, and then we'll try to prove the main theorem. So the setting I want is the following. I want a category which is so-called proper over S. So S is still the same as before. Now, what does this mean? So for this thing, I need some small enhancement to speak about base change. So if a category S, I can always base change it. And this I need some extra stuff. So for us to keep in mind, for us, D now should be the category of perfect complexes on X. Okay? So being proper, what does it mean? So by having the fact that it's enhanced, this means that I have a local home, which is a complex of sheaves on S. This is nothing, I'll comment in a second on this one. And so what I want this guy to be perfect on S. So that's the definition of proper. So concretely, if S is a point, it means I want the homes to be, this is a R home. You always have to think that I'm putting always an R in front. So I will not put it anymore, but this is some sort of R home. So being a perfect complex, this means that given two objects, the X are finite. Okay? So in this geometric context, this means the following. It means that X must be proper, but there is some flatness in this condition, which is of finite order dimension. Okay, so that's the condition of being proper for a category. So you have to imagine something like we have before we have flat. Here it's finite order dimension, we allow a bit more. Now D is the only category we can work with, and yeah, the whole proof is based on a few Nakayama lemma. So let me start with the first one, and then I'll try to finish them. This is the easiest one. It says that in this generality, it's not so hard to see that they have a complex and they have a point such that the restriction of E is equal to 0, then E is 0 in an open subset. Actually, we have 4 Nakayama lemmas. Essentially, that proof is based on 4 Nakayama lemmas. So this is the easiest one. Yeah. To the fiber of S, yes. Yeah. So I can always base change anything. It's like D behave like whatever you can imagine. So you can always base change whenever the scheme is nice. So quasi-compact separated. This is fine. And so this makes sense. Yeah. Okay, so this is easy. So the second thing we need is, but D is not a good category for us because T is the category of perfect complexes. So this does not have any T structure. So we need a bit more, and so we enhance it. We make it something slightly bigger, and again we use the fact that this is enhanced, so you can take all co-limits and create a so-called int category. And this I define it to be simple as Q co. Again, in the example that we have, dq co is dq co, unbounded over x. Okay, so if I start with x over s, this construction is giving you back the quasi-coherent shifts. Great. So now what is the point? The point is that in this generality I don't have a T structure to start with, so I have to construct that, and I have to find a way to construct what is dB. And so that's the way we go. So I take G alpha, some infinite but small set of generators for D. So generators means the following thing. Equivalently means that if I have an object here in DQC which have no x with all these objects, then the object must be 0. So that's one condition. Or equivalently, by a theorem of Bondal-Vandenberg, it says that any object in D can be generated by finitely many extensions and direct summands of these objects. Yeah. That's a good question, actually. I'm always hiding this thing. If we assume that now I can add some more assumptions. So the second assumption now to make work the theorem is Grothendieck existence theorem. So assumption 2. And so how do I state the Grothendieck existence theorem in this language? I take this category over here. So if I have a BM local Noetherian complete, then what I want that D, I base change to B, and I want this to be the same thing as the limit over n of D of B mod m to the m plus 1. This thing categorically makes perfect sense in this context. That's why we need this thing. And so this is exactly Grothendieck existence theorem. If I have, sorry, PC. Okay, so if I have a pseudo-coherent complex on each infinitesimal neighborhood, I have a pseudo-coherent complex on the limit. Okay, so that's what we want. Okay. And then there is a third assumption, which is quite kind of technical. Sorry, let me finish one more thing. So again, this thing over here, it's true in the geometric situations, but it's also true for when D is smooth and proper. So again, this is not a condition if under the assumption that it's smooth. Okay, so that's important. So there is no assumption there. And the third one, this is technical. This is telling you that for all base change A, as before of finite type over S, what we need that in the category DAB, which makes perfect sense, this thing has a so-called strong generator. Actually, we need some weakening of this thing, because otherwise it won't apply to supported complexes. But anyway, so that's a technical condition. I don't want to talk about this thing. This all is true in the geometric situation, and for some miracle is also true in the case of smooth and proper. So in the case in which D is smooth and proper, there is no assumption. Okay, but otherwise these three are the assumptions we need. And in the geometric situation, there is no assumption. And so here's the theorem now. And so the theorem is the same as the one. Okay, 5 minutes. Okay, good. And so the main theorem, the general version, so part 2, it's saying that the same as before, same as the main theorem, but in this generality. So now the factor is a T D over S, which is when I plug it into A. So this is the same as you can imagine. So it's a bounded T structures on DBA, which makes sense, which are compactly generated and in the preferred equivalence class and with Noetherian heart. So this is actually the main theorem. And so the theory says that this thing is represented by, as about tau prime, if you want. This is B. Okay, so that's exactly B. Yeah, thanks. Okay, so the same exact statement, but in this context. That's what we need, actually. Okay, and so how to prove it? Just 5 minutes to give an idea. And well, the proof is we have to define what the T structure should be, and you have to prove. So this is the same. So let me leave it here. At least we have the statement here. So it's the same, but with the condition that we have there. Okay. So how to prove it? So, idea of the proof, just 5 minutes. So we can assume safely that so we are over spec B, so S is equal to spec B. And for simplification, if you allow me, I call it 0 spec of B over M, which is the closed point in S. So how that proof goes? I need to use this all the thing we want. So I need first of all to do the construction in quasi-coherency. So I start with some T structure in D0. So D0 is D base change to B mod M with the property that I want. Yeah. Okay, I want to prove the surjectivity. The injectivity is actually not so hard as well. The only reason why it's not so hard because it was already proved, essentially. So the injectivity is proved essentially, well, it's not, okay. It follows by the same argument as by Abramovich-Polishuk. So it's another Nakayama lemma, a fourth version of Nakayama lemma. But I will tell you later, maybe. But I was going to prove the surjectivity, which is the part that actually is more useful for us. And I will comment also on the injectivity here. So whenever I have a T structure, I can also extend it, let me call it tau hat, to a T structure on quasi-coherent shifts. And the extension is just the same as what we defined here, for example. You just take the generator by D smaller or equal than 0. So this is a formal thing that you can do, the same as before. And so tau 0 hat. And now what is the possible definition? But as Sasha remarked, the pullback factor is right exact. And so we know that if I have a T structure which lifts this T structure on B, it must be defined as follows. So this is a definition. I'll comment in a second why it must be, but at least it must have some property. Let me call it tau hat. So this should be the following, should be the one generated by all perfect complexes such that if I take the restriction to 0, this is in D0 smaller or equal tau 0, 0. And then I close it up by direct sums and extensions. So the only thing we know actually by restriction, we actually know that there is an inclusion here. Okay? And so the whole point of injectivity of our statement is that actually this is the only one. If you ask that the category is Noetherian, here we need to assume that it's Noetherian. Yeah, so that's where we really assume Noetherian because otherwise it's not true actually. And so anyway, so the statement is that once I define this one, then tau hat is still in the same, is still in the preferred equivalence class. Okay, so that's the main things. And so the whole thing, the whole game of T structure is actually very easy. So you use quasi-coherent shifts and then you want to descend it. So we need to descend it to dB. This is B. All right, this is over B, to dB. So that's the easy way. And so for this thing, we need a fundamental result, which is this lemma, which is Nakayama. Sorry, I write the lemma and then I explain what is the intuition behind it. So this is the fundamental one. That is the hardest one. So let me take E, which is in pseudo-coherent, intersected dqc smaller or equal tau hat 0. Okay, so a complex which is supported in negative degree. And so the fundamental result is the following. So let's assume, that actually it is actually, so H0 of tau hat of E is non-zero. So a priori here is just a T structure on quasi-coherent. So the guy is coherent, but his cohomology, there is no reason which is coherent. So we want to prove it's coherent. So, but this is a priori is quasi-coherent. And so the key point is the following. Then, still, from the viewpoint of Nakayama, behaves like something which is coherent. And so then the H0 on tau 0 hat, sorry, this is badly written, of H0 of tau hat of E restricted to 0 is still non-zero. So this means I take this guy, I take the underived restriction to the special fiber. If this is non-zero, then this is non-zero. So this is not really Nakayama, right? Because Nakayama will tell you this is true if this guy is coherent. But we don't know yet. Okay? So maybe make an example. Just taking 1 minute and then I'll sketch the proof. I'll take one blackboard. So the example to keep in mind is the following. It's a triviality. So if I assume if I am over C of bracket T, I can look at the following resolution. And these guys, for example, this is a classic example we don't like, because that guy, when I restrict to the zero fiber, is always zero. And this guy is also we don't like, because this guy is only some Tor 1, but not. And so you can very well imagine, and it's actually true, that there exists a T structure for which the cohomology of this guy, which is perfectly coherent and nice, is as follows. So the zeroth cohomology is this guy. So this is the H0. And the -1 cohomology is our guy CT over CT. Maybe you have to shift it by -2, and then you shift it by 1. So this is H1. And so this one, we don't like it. Okay, so that's not, because that will never extend. So if I have a T structure like this, which exists, so this is coherent, but if I take H0 and I restrict it to the zero fiber, it has zero cohomology. Okay, so we don't want this example, and so this lemma is telling you that this example will never arise. Okay, so this example doesn't apply to us. And so that's the whole point of this lemma. And so once we have that one, then the proof is easy. And let me finish one line. And so how to finish the proof? Then just use Grothendieck existence theorem. Now it's and this lemma. So sorry, just make you one second. Sorry, I'm very late. That's a key point. So if I start with E in VPC intersected VQC smaller or equal tau hat 0, then I look at the cohomology in degree 0. And then what is the statement? The statement is that by using assumption 2, there is an exact sequence, exactly as this one. So it's a 0 goes into A hat, goes into A, goes into A bar, goes to 0 with the following properties. So this is coherent. So this belongs to DPC, and this one is not coherent a priori, but it has the property that H0 of A hat restricted to 0 is equal to 0. How do I obtain this thing? I obtain this thing by the assumption 2 as a limit. And now I'm done, because this is coherent, I can remove it, and so I'm left with a coherent complex whose cohomology in degree 0 must satisfy this condition. But the lemma is telling me that this cannot happen. And so this, by using Nakayama, implies that A hat is equal to 0. And so this means that A is equal to A bar is coherent, and then I do induction, and then my T structure descends. H0, I'm sorry. No, this proves that A hat is 0. Yeah, that's the whole point, right? Because this lemma, right? So, yeah, but this is in the heart, eh? This is the exact sequence in the heart, eh? In the EQC, in the heart. Oops. Sorry, yeah. So you're right, it proves that H0 is 0, but this is just a complex. Yeah, it's just a object in the heart. Yeah. Okay, sorry, I'm very late. Thank you very much. Sure. Applications. Yeah, okay, so applications. So application, we have 3 applications of this thing somehow. We have several applications actually. So one thing that we had was this question of realizing any hyperkähler, for example, of K3n type as a moduli space over something. And so that does the job. So how do we do that? So you start with of K3n type though. We start with that one. So how do we do that? We use Markman result. So there is a nice paper by Markman and Merotra that says start with a K3 surface and with some Hilbert scheme, let's say, no? Then you take a deformation of it, let's say polarized deformation. So what they construct, sort of, they construct a category which is an actual category, which is a deformation of the K3 surface. Now they don't really do that because the issues that they do, it depends on the choice of some algebra object. But some algebra object in the derived category is a bad defined notion. But if you have this enhanced thingy, then it is a well-defined notion. And so what we do this epsilon more and prove a version of this Markman-Merotra result in this enhanced situation. And now we really have a family, as I defined, of category, which is smooth and proper over a base, and now we apply our theorem, at least formally. And so it is telling you that T structure exists, that stability condition exists, and then you realize your very general fiber you need to as a modular space of the category. So plus a stability condition, but I didn't mention stability condition at all. But the thing is that once you have the T structure, the obstruction for the formal stability condition it's very mild, and in this context it's satisfied. So you can always do that. Yes, thanks. So that's I never mentioned it, but it's about this is the key part. The rest of the structure is automatic. It's not automatic, but it's almost automatic. Yeah. So that's one application that we have in mind, and that might be useful to several things. Realizing as a modular space, then it gives you something somehow. And then there is another application to K3s, to a conjecture of Bridgeland, to prove that the space of stability condition, well, we cannot prove it's connected, this was an old conjecture, but you can prove that there is no exotic stability conditions. And that's actually, it's an argument similar to what we did a long time ago with Daniel Huybrechts. And we need formal schemes, and for that condition we need these weird categories. So again, we cannot do it just by geometrically. And then there is application to Fano threefold, and that's another thing that we can, yeah, anyway, I can tell you later a bit. Sorry, I was out of time to write the applications. There are more actually, that is a technique actually, then also to construct stability conditions. So there are a few things that you can do with that. But the key point is really T structures. Once I have the T structure, then the rest is, yeah. Thank you very much. Yeah.